let's get started. Announcements. So today we'll keep going through digital logic, the building blocks of all computer systems. In this class, we focus mostly on combinational logic. So today we'll talk a little bit about sequential logic to kind of give you the whole picture of digital logic. The main task today will be to give you a quick start, a tour, and helpful tips, and a couple sections knocked out of programming assignment 6, which is now out finally. 2 weeks work time due during finals, May 10th. This is a very strict deadline, so you have to give me time to grade the whole class and then submit final grades. So do not miss this 2-week deadline. The goal is to practice with digital logic, right? So the contents we've been talking about the past couple weeks on how digital logic works, gates, and these different components of all computers. And then an additional fun aspect of this is a lot of the concepts that we had in this class will have some kind of reprise, right? So we'll have some of the recurring characters, like how numbers are represented, is going to appear again in this assignment, and caches as well will appear again in this assignment. So this, in many ways, acts as a cumulative assessment, cumulative summary, nice big concluding knot on this journey into computer architecture, right? Deeper and deeper into the internals and how computers work. Okay, so in terms of logistics, right? So PA5 is now officially all wrapped up. So I've been looking at kind of how the grades are going to work in this class. So basically, this class has 2 major assignment categories, right? The programming assignments and the quizzes. And for everybody, the quizzes averages are higher, or the quiz total is higher than the programming assignments. And then furthermore, the quizzes, we had 7 quizzes this semester, and it's set to drop the lowest quiz score that you got, right? So this is additional kind of flexibility in terms of you wrapping up the quizzes, right? So overall, when all of the grades are in, all the scores are in, as far as how I'm going to be assigning letter grades, for the most part, you can expect the numerical score that you see on Canvas to be your final score, right? The way I will add, quote unquote, a curve or some flexibility is I may increase the relative proportion of the quizzes just so that some of you would get an extra boost kind of beyond the border, right? So I may be adjusting kind of how much the quiz average counts toward your final grade. And the way it may be adjusted is quizzes might count for more than they do now. And that will universally help anybody who's using that flexibility. Cool. Okay, so any other kind of logistics questions before we move on? Very good. So we've talked about how digital logic, there's 2 categories, combination and sequential logic. Combinational logic has no state. This is how you calculate values. Sequential logic has state, right? It's the logic circuitry that keeps track of data over time. For the most part, what we're covering is combinational logic. We've dealt with sequential logic in this class so far, but as far as the programming assignment and kind of our exercises go, everything is in the combinational logic land. So all combinational logic is constructed of gates, of which there's just a few basic types, right? So there's the AND gate, OR gate, the NOT gate, the NAND, NOR, XOR, and XNOR gate. Just a few handful of basic gates. You can look at the slides from last week for a full coverage of all the types. One important one among them is the XOR gate. Right, the XOR gate is nice and balanced, symmetric, equal. Right, so the XOR gate basically is 1 if the two inputs A and B are not equal. And so if you look at the XNOR gate basically acts as a kind of comparator. Right? It compares A and B, and if they are equal, then the output of XNOR A and B is true, is 1. And so we can see this in action. So let's now move on to a programming demo and also a tour of programming assignment 6. Okay, again, any private messages on the Zoom chat is actually not that private because it gets projected on the screen. Okay, so programming assignment 6. Right, so it is now released on Canvas. You access it in the same way as the other programming assignments. So you go to the 2022 directory, git pull, and you'll have the components of programming assignment 6. What you see is going to be a little bit different from what I see. I have more directories here. The first piece of programming assignment 6 is called comparator. Right, so comparator asks you to implement a comparator. And this is going to be very different now because none of these assignment parts are going to ask you to write any C code. So as far as writing C code, we're done with that for this class. No more C. You know, almost certainly somebody is very happy that there's no more C. You'll encounter C in the future in your career. The assignment parts here, what you'll be writing in is to create digital logic. And so the digital logic looks like this. Okay. So the digital logic looks like this. This is a syntax that is actually a valid form of a language called Verilog. And Verilog is a digital design language, a hardware design language that computer engineers, computer scientists, electrical engineers use to implement digital logic, digital hardware. This is a very limited subset of the Verilog logic, Verilog syntax, but nonetheless, this is valid Verilog. Right? The real Verilog has a lot more constructs in it. We use a small subset of that whole language. In a logic description file like this one, there's 4 kinds of lines. Right? So the 4 kinds of lines are input lines, output lines, wires, and assignments. Right? So when you see a file like this, you can think of kind of drawing a hardware box. Right? You have a hardware box. On one side, you have all the inputs. On the output side, you have outputs. Or the right side, you have outputs. And this piece of hardware, you have several wires going in. Right? In this case, we have 2 sets of wires going in called A and B. A and B. And furthermore, both of these numbers are 2-bit numbers. Right? So we denote this with this syntax that's special to Verilog. This is called 1 down to 0, meaning that A consists of 2 bits. One of the wires is called A1. The other wire is called A0. So we say this is 2 bits wide. This means that A1 is 1 bit, and A0 is the other bit of A. The next category of lines or specifications in this language is the output. Right? So on the output end, on the right side, we have a wire coming out. It's a single wire called equal. And equal is just a single bit, so it doesn't have a bit width specification. It could, right? There are parts of this assignment where you'll have outputs that have multiple bits, and they'll follow a similar syntax as inputs. Okay, so any questions so far about inputs and outputs? Yeah, Donald. Yeah, so if it's a 3-bit input, it would be 2 down to 0. These indices are inclusive, which is kind of a little strange thing about how these things are indexed. Cool. Okay, so your task, or at least as far as this demonstration code goes, the task of this demonstration code is to fill in the combinational logic inside this box so that equal is 1 when A and B are equal, and equal is 0 when A and B are unequal. Sound good? So what are ideas on how to implement this? Okay, so we're jumping ahead. We're mentioning the XOR gate. Right, so is there a way to kind of decompose this problem? Right, if we want A and B to be equal, A and B are both 2-bit numbers. One way to think about how the problem decomposes is that, well, each of the individual bits should be equal. Right, so equal is going to only be equal if the 0 bits are the same and the 1 bits are the same. So that's what we see in the code here. I'll introduce this category of lines called assignment lines, assigned lines. And the syntax of this is I'm going to assign the output bit equal to be the AND of this wire called bit 1 equal and this wire called bit 0 equal. Right, so the ampersand here is the same as C syntax. The ampersand means AND, logical AND of these 2 wires. So great, right? So these 2 wires, I want them to encode if either the 0's bits are equal or the 1's bits are equal. And so we also have to calculate the values of these 2 wires. Right, so that's what we do in these 2 other assignment lines here. The first assignment line says bit 1 are equal, the 2 1 bits of the 2 inputs are equal if A subscript 1, A bracket 1, is equal to B bracket 1. Now, this operator here is how you express XNOR in this description, right? Why is it XNOR? Well, it's basically the XOR, which just like in C is denoted with a little caret, and tilde means inverse, negation, right? So this is negation of XOR. And we can go to our slides here to reference, right? The negation of XOR is the XNOR. And we talked about how the XNOR basically implements equality. If A and B are the same value, 0, 0, or 1, 1, then the XNOR gate is true, is 1. So that's to compare the first bit. And then the second line here is to compare the less significant bit, the LSB. And with those kind of intermediate values calculated, you can find equal overall is the logical AND of both of these. So finally, I'm going to introduce the last category of lines, right? The fourth type of description line in here, which is if you want to invoke some temporary value, some temporary wire to carry values, you have to declare them using this syntax here saying wire bit 1 equal, and later on you can assign them to different logic values. Okay, any questions here? All right, we can kind of do an exercise here of drawing the internals of this. Right, so we have A coming in. Do this separately. On the input side, we have A1, A0, B1, B0. Right, I've taken apart those A's and B's into the constituent wires, now constituent bits. Come inside here, and I've got two XNOR gates. Okay. I think I need to draw this more stylistically. The XNOR gates have this wavy design here. XNOR gates A1 and B1 go into the same XNOR, and then A0 and B0 go into the other XNOR gate. And only if both of these are true using this AND gate, then equals is true. So basically, we filled in this box here where the boundaries of this module, this combinational logic module, is surrounded by the square box I just drew. The inputs are on one side, the outputs on the other. The gates are contained inside the combinational logic. And I've got these temporary values. This is bit 1 equal, and this other temporary value is bit 0 equal. Right, and because I have these temporary values kind of declared here, I need to specify it in the description language that I've got these wires. Okay, any questions about the specification of the circuit here? Yeah. Okay, so your question is if A0, B0 are both 0, how does this compute whether they're equal? Okay, so the question kind of is diving yet deeper into the electrical, like the electrical implementation of these gates. And it's true, right? All these values are encoded as voltage levels. And just because the voltage level is low or 0 doesn't mean that this gate completely shuts off or becomes disabled. Right? The gate responds to high and low voltages, and it computes the correct output depending on if its inputs are high or low voltages. Sure, right? 0 means logical 0, right? We're working at the logic level here, not necessarily at the current and voltage level. Okay, so how do we test this out, right? So, like I said, these are not C program files. These are not C source code. So in this assignment, there's no notion of compiling code. Instead, this logic that you write is input to a simulator, right? So very similar to programming assignment 5, you have access to a simulator in the PA6 directory. It's a executable, right? So you don't see the source code for this simulator. The simulator tells you that the way you use this program is you invoke /circuit simulator, invoking the simulator. Then you give it the circuit file, which is this here, is your circuit file, the .v file. So let's try that, right? /simulator, and I'll give it comparator provided .v, the digital circuit description. And it's going to tell you that not enough input values to match the number of inputs in circuit file. Okay, so number of inputs in circuit file here is I've got two variable names, right? A and B. And so when you invoke the simulator, you have to tell it what the values of A and B are. And you give it to it on the command line here. So after specifying the circuit file, you can say A is 0, right? So the first number you input matches the first input line. And then you say another 0, which matches the second input line. So this will have told it that A and B are 0 and 0, like this. You then invoke it. It tells you, upon reading the circuit file, it saw 2 input lines, 1 output line, and after executing the circuit, simulating the combinational logic, it finds that equal equals 1. The equal is 1 because A and B in this case are both 0, 0. Yeah. Yeah, right. So this is a very limited subset of Verilog, just for combinational logic. A real Verilog, like I said, this is actually a syntactically correct subset of Verilog. So if you feed this to a Verilog synthesizer, it will understand this. But the circuit simulator I'm giving here only recognizes this limited subset of Verilog. And so more advanced constructs will not be understood. Yeah. OK, great. So let's give it another set of inputs, right? So we can also say, for example, 3, 3, which says these two 2-bit inputs each are 3, 3, meaning to encode 3, right? This will be 1, 1, 1, 1, encoding A equals 3, B equals 3. And the Boolean logic figures out that A and B are indeed equal, 3 equals 3. So the equal output here is once again equal equals true. You can give it something else, right? So A equals 3, B equals 1, and it'll tell you that the two are not equal. Great. So the task for part 1 of programming assignment 6 is to take this and implement a 4-bit comparator. So how might we modify this to become a 4-bit comparator? Okay, what are ideas on how to make this a 4-bit comparator? Right, so I want to make this a 4-bit comparator. So what should we do first? DJ. Okay, so first of all, the inputs are now 4 bits. So the indices are going to be 3, 2, 1, 0. So these will have to become 3 down to 0, making these 4-bit input, 4-bit input. Does the output change with? No, right? Equal is just a true-false value, so it's always just 1 bit. What we'll probably need to do is, OK, so now equal is going to be some combination of 4 bits here, right? So 4 bits all have to be equal. So we can say it's going to end up looking something like this. The final value of equal should be that bit 3 is equal, bit 2 is equal, bit 1 is also equal, bit 0 is equal. All 4 cases ANDed together, indicating they're all equal. We can then also calculate these intermediate values. So bit 3 has to be equal, bit 2 has to be equal, and they're computed from A bit 3 has to be the same, B bit 3 has to be the same. Bit 2, A bit 2 has to be the same, B bit 2 has to be the same. And what's missing here? Yeah, so the way that the syntax works is if you want some intermediate value, you have to declare that the wire exists. So you've got to also declare wire 3, wire 2, bit 3 equal, bit 2 equal, all also exist. Okay, so there's one more thing here, right? So one more thing is in this subset of Verilog that we're writing, I'm only allowing 2-bit input gates. So here we have, what's this? This is a 4-input AND gate. So in the slides before, we talked about how you can construct multiple input AND gates or gates by compositing them, right? So a 3-input AND gate is really just, well, you put them in series. You find A and B equals, A and B is the AND gate of that is true. Then you feed that into yet another AND gate, and finally you will have A and B and C. And here's the truth table to that effect. So in the source code here, how do we fix this? Right? I'm only providing 2-bit input AND gates or just gates in general. So how do we modify this? Yeah. Okay. Okay. Cool. Right. So what we have to do is you have to split it out into some more wires to aggregate the results. Right. So I'll assign to a new wire that I'll declare here. Which I'll call 3 and 2 equal. It seems like a sensible name. Right. So 3 and 2 equal is true if bit 3 is equal, the bits 3 are equal, and also the bits 2 are equal. And now that I've made that wire, I can substitute that in, replace that there. And still I have what's remaining is a 3-input AND gate here, which is not allowed in the syntax. So I need to create yet another supplementary wire, which is now called 1 and 0 equal, which will be the conjunction of these two cases. And now that I've prepared that wire, I can put that in. So now I've just got a bunch of 2-input AND gates. Okay, this should be good, right? We try running it? Yeah. Still have to declare the wires, right? So let's just see what happens if we try running this. So I'll invoke the circuit simulator with this comparator, 4-bit comparator that I've just implemented. And it's going to tell me that, okay, you invoked circuit simulator provided, so this provided circuit simulator. You gave it this digital logic description, comparator.v, as input. I'm telling it the first input, A, is 3. The second input, B, is 1. It tries to read this. It's happy. It says read 2 input lines, read 1 output line. Great. It's scanning through this, and then it sees this variable called 3 and 2 equal. So it sees this line here. And it says this is not found in variable declarations. Right? So this is complaining that we invoked this wire here, which was not previously declared. So just to fix that, you should say wire and wire to tell it that I'm invoking these wires. Great. So let's try it now. And this time around, it's happy. It read through the whole file. It computes what equal should be. So A is 3, B is 1. 3 does not equal 1. So equal finally is 0. Any questions here? Yeah. That's right. All right, so for 2-qubit gates, sorry, not 2-bit gates, this is classical computing here. For 2-bit gates, the syntax here is assign the output destination equals the first input and the second input and the ampersand in the middle, the gate. Cool. Any questions here, right? So just like with any pieces of any of the assignments that we've been doing in this class, you can invoke the autograder. So the autograder will test it against a fixed set of inputs that you can see in the test directory. Right? So let's look at the test 0 that you can see. Test 0 just records 2 lines. This is saying that A equals 0, B equals 0. And the expected output of test case 0 is that equality is true. Right, so if you're debugging, you can use this as one mechanism to go see what's going on or what's the expected answer. If you run the whole autograder, it runs through 25 cases and it prints out the expected results in each one and your result that you gave in this line here. Cool. Any questions about this part 1? Yeah. That's right. All right. So the indexing here, this is an important question about this. If I gave it A equals 2, for example, if A equals 2, the value A is 2. Oh, this is 0B1, 0 is a 2-bit number. And you'll see that A subscript 1 is going to be 0B1, A subscript 0 is going to be 0B0. Right, so the higher index is the MSB, is the more significant bit. 0 is the LSB, the least significant bit. This is the convention that we're following in this assignment. Right, and that's reflected in the syntax here for Verilog, right? So the syntax here of 3 down to 0, this is the Verilog syntax for expressing that this should be a big endian encoding. The high order bits, the more significant bits they come first. Okay, great. So that is basically how you do the first piece, right? Comparator digital logic for 2 4-bit numbers, comparing them for equality, right? And so the description here basically walks through what I just demonstrated. Cool. Okay, so on Thursday, we talked about how there's this notion of universality or completeness, which is that if I only give you NOT gates, AND gates, and OR gates, you can use that set of gates to compute any Boolean function that you want, right? And this is a underpinning of why computers can do many different types of things. because you can take any logic function, any kind of computation that you wish, and distill it down to these simple gates and wire it together as an electronic circuit like this. And so the cast of characters that we're dealing here is the NOT gate, the AND gate, the OR gate. And we talked about how for any function that you wish, given some set of inputs, you can implement that logic by following a few types of set recipes. Right? So one type of set recipe is this one here called the sum of products form, where you find the sum of products. Right? So sum here in Boolean arithmetic, the sum corresponds to OR gates, and the products correspond to AND gates. So in other words, this is expressing a function as OR of AND, right? So this function here, D, subjected to inputs A, B, and C. A, B, and C are all Boolean, right? If the D function is this expression here, well, this expression right now is put in a sum of products form, right? It's a OR connecting together two ANDs, A and B and C, and B and C, like so. So one concrete exercise that we did to show how this works is we talked about a 7-segment display, right? So 7-segment display is a way of displaying decimal numbers, base 10 numbers, base 10 digits. And each of these segments light up for different numbers, right, for different digits. And as it turns out, the segment that lights up the least often is this one here. So these, in this convention that we're using for this class and also some other literature, these segments are labeled A, B, C, D, E, F, G. And the one that lights up least often is this one, E. Right, so for which numbers does E light up? Yeah. 0, 2, 6, and 8, right? So E lights up for 0, 2, 6, and 8. And so the second piece of programming assignment 6 is called, well, let's go to the description here. The second piece of programming assignment 6 is called 7-SegmentDisplayE, to implement the logic that drives that segment there. And the interface for 7-SegmentDisplayE, well, is in the provided code here. Okay, is in this provided code here, right? So inputs and outputs. Right, so the input to this box is the number you intend to display. Right, so just kind of to put this concretely, you're asked to implement this digital logic, combinational logic here, where if I give you the input is a number of the digit you intend to display, this has several outputs, right? There's several wires, one of which goes to this E here to decide if E should light up, depending on what the number is. And so anybody want to quickly explain why this should be a 4-bit input while I write out a truth table on the board? Right, why is this a 4-bit number? in order to capture the value, I guess, right? So the number of valid base 10 decimal digits are, well, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? Base 10, 0 through 9. And each of them correspond to some binary encoding given in num bit, right? So this will be 0, 0, 0, will be 0, 0, 0, 1. Right? If it only were 3 bits, well, you would have stopped at 7, right? So we need the 4th bit to be able to represent 8 and 9. And you can ignore the rest of the rows here, 10 through 15, because we're only concerning ourselves with decimal digits here. Okay, so what's the approach to implementing this logic here? Sum of products, right? So the E logic here is going to be a sum, an OR, of logic that detects if it's 0, 2, 6, or 8. Right, so the relevant rows that we're looking at here are 0, 2, 6, and 8. So in order to represent these rows, well, we'll have to find something called a min term. Well, min term is just this jargon that denotes an expression that detects this row, right? So an expression that detects this row is going to be something like not A3, I guess it's num3, not N2, not N1, not N0. Right, so if you plug in 0, 0, 0, 0 to this expression, 0 not 0 is 1, 0 not 0 is 1, 0 not 0 is 1, 0 not 0 is 1. This expression here becomes becomes 1 and 1 and 1 and 1. So this will evaluate to true. Right, so it means that this expression has detected that the decimal that you're giving in num bit is 0. Right, so the rest of these items here are going to be N, N1. This one is true, indicating that this bit should be 1. And N0 negated that. And let me just fill out the rest of these rows here. Negation, negation, negation. Great. So we've laid out a kind of expression-wise a template for how we should implement this logic, right? So the goal of, again, this assignment piece here, 7SegmentDisplayE, is to fill in the digital logic that drives this output called E, a single bit output E, that decides if this segment should light up. Right, so let's work on this together. Right, so as with any assignment piece, you copy the, or you move the provided code into the code that you want to have executed. And this is no longer C source code, but rather this circuit description .v file. And we've given some hints, right? So I've given some hints on what are some useful wires that you'll need. Right, so the first set here, let's focus on the assignment lines. Right, so the first set of lines we'll look at is these assignment lines, which basically take each bit of the numeral and immediately negate them. Right, so I take the numeral bit index 3 and negate it so that I have not numeral bit 3. Now, wires, I don't have this array or indexing syntax. So if you need multiple wires in this bundle here, you'll have to manually declare not numeral bit underscore 3 and do that for 2, 1, and 0 like this. This syntax here denotes a 1-bit input negation gate, right? So this is this bit here negated and stored in not numeral bit 3. Okay. So very good. Now, what I would want to do next may be something like let's work backward through here. All right, so if we were to work backward through, well, which cases should E light up? Well, E should light up for a summation or a conjunction or of all these cases, right? So I would call this minterm 0, minterm 2, minterm 6, minterm 8. I would want to OR them all together. And so you may want to write something like this, right? Minterm 0 or minterm 2, minterm 6, minterm 8. But again, I don't offer multiple bit gates. So it would complain that it doesn't understand the syntax. So you have to split it out again so that you have additional OR gates supporting this expression here. So you may assign a new wire called this. Right. So now this reduces this into a 3-input OR gate. And 3-input OR gates are still not supported, so I need to create yet another supplementary supporting wire. A reasonable name for this would be, well, minterm 6 or minterm 8. You place that in, and now you have created 3 OR gates to fully realize the expression for E. Right, so any questions up to this piece here? Okay, so what's missing still? Right, what's missing still? Well, we still need to get from the numeral bits into figuring out the minterms, right? I've only filled out kind of some auxiliary code to find the negations, And I've summed over each of these terms here. So now I still have to implement this in detail. Right, so how do we do that? First of all, do you guys understand what's going on here? Yeah. Y, 0, 2, 6, and 8. Right, so we're driving this segment here. Right, this is an 8-segment display. And for what numbers does this light up? Well, does it light up for 1? No, right? If the digit being displayed is 1, only B and C light up, 1 over here. Does it light up for 3? Right, if it's 3, the way the 3 is displayed is 3 is displayed here, right? 3 is displayed there. So A, B, G, C, and D would light up, but not E. Right, so the only digits that E lights up are 0, involving the outer segments. 2 would light it up. 6 would light it up. And 8 would light it up. Which means that to drive this E segment here, you need to detect if these numbers are being inputted. These numbers are represented with this expression here. And then what you would do is you would take each of these and feed them into a OR gate so that if any of these are true, then the segment E lights up. Cool. Okay, so we still have to get from these little bits here to realizing detecting this. Right, so this is called minterm 0. So minterm 0 may look like, well, minterm 0 is not bit 3, not bit 2, not bit 1, and not bit 0. So basically we would do that, right? So not bit 3 and not bit 2 and not bit 1 and not bit 0. And again, this is a 4-input AND gate now. Right? So we have to decompose that into at most 2 input AND gates. So we would do something like this. Substitute that in. So now we have still a 3-input AND gate. We'll decompose that some more. We'll substitute that in. So now we've taken what was originally a 4-input AND gate and turned it into 3 separate 2-input AND gates. Good. Right, so that's how you compute minterm 0, 0. So what will be required to finish the rest of this part of the assignment? Yeah, DJ. Yeah, so we still have to keep doing that for the other minterms, right? So you would do something like assign minterm 0. What do we need? We need minterm 2, right? Assign minterm 0, 2 equals, and how do we express minterm 0, 2? Minterm 0, 2 is not 3, not 2, 1, not 0. So it would look something like this. Not 3, not 2. We'll just copy that down. And 1, right? So instead of taking the negated 1 there, I'll take the positive not negated 1, numeral bit 1, and not 0. Right? So this would be an expression for midterm 0, 2, but again, this is a 4-input AND gate, so you would decompose that some more. Make sense? So that's basically how you would go about part 2, right? 7-segment display E. Any questions here before we move on? Cool. So we'll keep kind of have a tour through what the assignment entails. Right, so that's part 2, 7-segment display E. Part 3 is a little trickier. Right, so for part 3, instead of doing the work for this one here, we're going to do the work for C, this bottom right display segment. Right, and as it turns out, while E was the least used segment, C here is the most used segment. Right, so if you think about it, which digits would C light up for? Does it light up for 0? C lights up for 0. Yep. It lights up for 1. Yep. 2? No, 2 snakes around it. Right. So it does not light up for 2. It does light up for 3. It lights up for 4. It lights up for 5. It lights up for 6. It lights up for 7. It lights up for 8. And it lights up for 9. Right, so the curious thing about this segment here is it always lights up unless it's 2. And so because of that, for the logic for display segment C, you would want to potentially follow a different approach. Right? So the clue to what's the easier approach for this particular piece, for this particular case here, is, well, if you have something that very often displays, you would want to switch to a different methodology called product of sums. Okay, so originally here we were doing sum of products. There's a dual. There's a dual called product of sums. And you can read about that here. It's a very similar approach, but just kind of like something kind of flipped around. And you'll want to express it as a product of max terms. Right? So following this approach will help you solve part 3 with fewer lines of code. Right? That's just a suggestion. Of course, you can follow the same approach that we did for assignment for part 2. That would just be more lines of code if you kind of turn it on its head. Right? Turn it on its head because C lights up very often and only not lights up for 2. If you flip it on its head, you'll have fewer lines of code to get the same outcome. Cool. So that's part 3. Any questions so far about 1, 2, and 3? Yeah. Can I do sum of products for That's right. So what if you just did sum of product for 2 and just negated it? Well, this is not a complete table, though. Right? Keep in mind, this truth table, because it's a 4-bit input truth table, there's a few more lines down here for 10, 11, 12, 13, 14, 15 that you'll have to account for to make that work. But that's an idea. You can experiment with it. Great. So that's the tour of part 1, part 2. Yeah, somebody on the line that wants to ask a question? Okay. So the other half to digital logic that we kind of don't have the kind of ability to cover more fully is sequential logic, right? So sequential logic basically is the way in which digital logic stores state, right? So in something like a cache, for example, in something that looks like a cache, well, first of all, is a cache combinational logic, or does it involve some sequential logic? Does a cache store state? Right, so we have a cache here. The cache has sequential logic. Right. And we talked about the sequential logic. Well, this is stuff like SRAM, right? Cells that store state across time. And that's what holds on to the cache contents. This output of the storage feeds into some combinational logic here. They interact with each other. And so you can think of the cache as being some combination, some integration of combinational logic and some sequential logic that stores state. And basically in programming in 7.5, you've already written a software simulation of how a cache operates. So what are the inputs and outputs to a cache? Well, what should the cache receive? Yep. Address. Okay. That's the most important one. What else? Well, maybe the data. Okay, somebody said the tag. Right, so where does the tag live? The tag is a piece of the address. Right? Remember, you have the address. The address is separated into several fields. There's the tag, the set index, and the block offset. So the memory address covers the tag already. Well, there's the data that you want to write to the cache. So this is write data. And maybe you also need another wire. You need another wire that basically says write or read. Right? You need to tell it that this address that you're giving to the cache is your intention to write to the cache, or are you just trying to read from the cache? Right? So there's a control bit here that says, are you in write mode or read mode? What's the output of the cache? Data, but specifically what kind of data? Right? The cache will output data to the CPU or to the rest of the CPU if it's a write or read data. Yeah, so this would be read data. Right? Data that is read from the cache, which you want to put into a CPU register elsewhere. Cool, right? So this is an abstract representation of what the cache is. And for parts 4 and 5 of the programming assignment, your task is to implement this combinational logic here. This combinational logic here. Okay, so let's make this more concrete, right? So what would that combinational logic look like? Well, I've given you a example demonstration code called directMapped, which is fully implemented. Okay, so this is not a assignment task here. You can go into directMapped, you can run the autograder. This is already a solved cache logic, right? So this runs all the test cases. This is a fully implemented logic for a direct map cache. So what does it mean for a cache to be direct mapped? Yeah, okay. For each set, we have exactly one way. Exactly, right? So this direct map cache here, has how many sets? Well, 2 sets, right? Set 0 and set 1. Okay, what else can we deduce about this direct map cache? We can go through the kind of whole rigmarole of saying things about this cache, right? The cache has a few properties. Number one, it has how the addresses are allocated. Right? So the number of bits in the memory, the number of bits in the tag, little t, the number of bits for the set, little s, and the number of bits in the block offset, little b. The capacity of the cache is going to be the number of sets, the number of ways, and the size of each block, SEB, capital S, capital E, capital B. So let's try figuring out what this is. All right, so first of all, what's the size of the memory addresses? It's already specified here in this description, right? Yeah, 2 bits, right? So very small memory addresses, just 2 bits. Can we figure out tag yet? Yeah. Yeah, 1-bit tags, right? So you can tell that's 1-bit tags because the tag fields here are 1 bit, 1 bit. What's a little s? Number of set bits, set index bits. How many sets are there? 2 sets, right? Set 0, set 1. So in order to index into set 0, set 1, it's just 1 bit. And remember, m equals t plus s plus b, right? So that leaves us with b is 0. Strangely enough, this cache design has no bits dedicated to block offset, which means that the way that the data is stored is you store exactly 1 byte in the cache as a single block, just 1 block, just 1 byte block. Cool. What's the capacity? Capital S is to the power of 1, so 2 times E, how many ways? Well, 1 way, right? This is a direct map cache by definition. It has no ways in it, just 1 way. So little capital E is 1. And the size of the block is 1 byte. So 1, this is a 2 byte capacity direct map cache. Okay, what other little metadata does it keep track of? Well, just like in programming assignment 5, we have the valid bit, valid, and valid. And each of them has a tag, right? So you can think of this combinational logic as I take this, right? So this is a picture of the sequential logic, what's being stored as state as the cache. This belongs in here. And what you're writing is this combinational logic here. You're getting from the sequential logic, you're getting from the storage, all of these fields, right? Just all these wires that record what is being stored. You have the valid bit, the tag bit, the data blocks, and you do this for both set 0, set 1. This comes into you as a input to your combinational logic. From the outside world, you also have the address that you're trying to access. And your task is to figure out what that output should be. Right? What should the output of this whole cache be in response to what's being stored in the cache? What's the address that you're trying to access? What is the data that should be provided? Any questions about the environment that we're working in here? Yeah. Sorry? Okay, so what should the read data be if there should be a cache miss? Right, so in this one, the output here, we have two sets of outputs. One is called read hit, right? So read hit is the same logic that you've been writing in programming in 7.5, right? What's the conditions for a read hit? And if read hit is 1, indicating like, yeah, indeed, the cache found the data for this address that the CPU is accessing, then it's a hit, right? Output to the read byte here, the data that is being stored. Now, if it's a read miss, this will be 0, right? It's not a hit, it's a miss. In which case, whatever this data is unimportant, undefined, right? So it could be anything. Right? So in many senses, this read hit bit indicates whether or not this output here is valid or correct. That's right. So two wires here. One is read hit. The other is the data, read data, which is 8 bits. Okay. So like I said, right, so this directMapped cache demonstration code is fully implemented, right? So you can study this fully implemented code to see how it implements the right logic for this directMapped cache. Right, so a key insight to what's going on here is essentially this is a multiplexer. Right, so a multiplexer means I've got two sets, set 0, set 1. And depending on what the set index is in the address, you only care about either set 0 or set 1. Right, so what is the set index here? Little s is 1. The address is 2 bits. So B is 0. Right, so the set index is really just the address, the lower bit of that. Right, so the lower bit of that address is the selection bit for if you want to access set 0 or set 1. If that bit is 1, you care about set 1. If that bit is 0, you care about set 0. And these selector bits, right, these selector bits go into this set of lines here, which is basically a multiplexer. Right? It's a multiplexer in that you narrow down the lines just down to one wire called valid. And valid is a selection, it's a switch, it's a toggle between if you want to see set 0 is valid or set 1 is valid. So you've taken these two bits here, the valid of set 0, the valid of set 1, and then depending on what the address 0 bit is, the 0th bit of address is, you combine these two wires into just one wire that's appropriately selected based on this wire here. Right, so that's basically all there is to the direct map cache logic. Any questions here? I'll let you stare at it for a little bit. Okay. So how do we explain what's going on in this line here? For these couple lines. Right, so I've got 2 bits in the address. The lower bit, the bit 0, is the send index. What's the other bit? The tag, right? So this tag here, right? So the tag from the read address needs to be equal to the tags that you're pulling out from the 2 sets. If they're equal, right? This is the comparator here now. If they're equal, then match is enabled, meaning that indeed these tags match the address that you're accessing. Okay. And the rest of the logic is a lot of kind of repetitive, kind of iterative code of just selecting the 8-bit block data from the cache, right? Because this is all 8 bits long, it ends up being many lines of code because you have to go through all 8 bits, 7, 6, 5, 4, 3, 2, 1, 0. Okay. And so all this is just narrowing it down so that the final result, the output, read byte, is just pulling from the data here. Cool, all right? So this direct map cache example here should be helpful for parts 4 and 5 of the programming assignment 6. Right? Programming assignment 6, parts 4 and 5 are, again, about caches, but this time around, it's the same cache ideas, but this time around, you're kind of visiting it at a farther, deeper level, looking at it in terms of hardware and how hardware would wire together to implement the caches that you've been studying. Okay. So basically, that's all there is to it, to digital logic, right? So digital logic, these little bits and bytes, gates, wires, this componentry, the storage devices come together to build the computers that we've been studying, right? So the caches that you studied in PA5 is really just physically implemented as logic that looks like this. All right, so we'll come back on Thursday and we'll do a lecture on advanced topics of computer architecture, right? So what are kind of like the broader directions of computer architecture and what are kind of the topics that are what you would study in kind of like further study in computer architecture in general. Okay, so good luck and I will see you on Thursday.